Thanks, Ian, for lightening the mood, and to the organizers in general for having me out here. So this is all work in progress, and it is joint with these three people, two of whom are helpfully in the audience and would be happy to answer any questions or concerns you might have about the talk while it's being given. So what are we talking about? We're talking about contact structures on three manifolds. So let's use the same notation that's been set up throughout the rest of the day. We'll have a closed, smooth three manifold. It will have on it a contact structure. And we'll use C again. So as we saw, this just means that it's the kernel of some one form satisfying this non-integrability condition, alpha, which d alpha should be everywhere greater than 0. And so I guess in a conference about contact structures, I really don't need to motivate the study of contact structures, but just for the types we're talking about here, these ones that fit into this murky world of being neither completely flexible nor completely rigid, I should say a little bit about where these terms come from. And it's really from the role that contact structures have to play in four-dimensional, defining invariance for smooth four-dimensional manifolds in this sort of post-Donaldson world where one's trying to, it takes a four-manifold that has some geometric structure on it, should usually have at least an almost complex structure, J, and you'd like to sort of borrow a tip from the smooth manifold world, cut it into slightly easier to understand pieces. Doing so, what you get is contact manifolds on the boundary. And so you're keeping track of things by understanding these contact structures and sort of maps between them induced by the cobordisms. So this brings the question of, given a contact structure, how much geometry can it keep track of? So how rigid is it? And this brings us to these two dichotomies that were introduced in Jonathan's talk, and a little bit in the last talk as well. The first one being that of over-twisted versus tight. And so, of course, over-twisted ones are the ones that are completely flexible, which just means, as we saw, that they're the same thing, thanks to Eliashberg. Say this is just a one-to-one correspondence over twisted contact structures and homotopy classes of plane fields. Homotopy classes of plane fields, by which we mean there's a unique isotopy class of over twisted structure in each such homotopy class. So they really have no role to play in this story over here, right? We can completely classify them by algebraic geometry. So if you're not over-twisted, you're tight. So you have some potential for being more rigid. And sort of on the other end of the spectrum, we have this dichotomy between things that are non-fillable and fillable. Where fillable here means that there's some, what we say, your null cobordant in your favorite geometric category, which is usually Stein or symplectic. Which means that you're the bottom end of that picture over there. So you now have some four-manifold, Stein symplectic manifolds in particular have almost complex structures. And on the boundary, we have some manifold M, and we can look at the complex tangencies. And so if your manifold is contactomorphic to such a thing, where this is the contact structure, then you are fillable. And so work of Gromov and Eliashberg tells us, let's do it over here, that fillable structures are tight, but then there are a lot of structures which sort of fall in the middle. So schematically, we think of looking at all contact structures. We have sitting in them the tight ones. So this is all contact structures. Tight ones strictly contained in that. And then in the middle, the fillable ones. So out here, the over-twisted world, again, we know everything about that. The fillable ones, that's really a question about Floer manifolds. And so you're left with this sort of murky stuff in the middle here where you don't have either of these things to fall back on. And so there's several approaches to studying this problem, most of which we could say fall into two camps. You're either approaching it via an entry through this frontier, so sort of a topological question. Are you tight? Are you over-twisted? Do you have an over-twisted disk or not? And try and refine those methods to work your way in. On the other hand, you could sort of go from the other way and start looking at more purely four-dimensional methods like pseudo-holomorphic curves and whatnot, and again, try and work your way down. And so just some brief description of the history involved here. Most of which can be described using the following frameworks. You're looking for some function, some way to assign to a contact manifold a natural number, possibly infinite, such that the zero set should be the over-twisted ones, the one at infinity should be fillable, so you're choosing what kind of fillability you're interested in, and then you would want ideally, some sort of cobordism relations. So if you have, say it like this, if, let's see, M1, C1, let me say it like this, because these are directed cobordisms. So if there is a cobordism, again, with whatever geometry on it, from M1, C1 to M2, C2, then you would like, ideally, f C1 to be less than or equal to f of C2. Okay. So this is sort of your full wish list that one would love to have. And there are some partial results to this, or partial answers to this. The first of which we could say is due to Jrue, this notion of torsion of the contact manifold, which I won't say anything technical about. I will say it satisfies just a couple of these things. So if you're over-twisted, you have Jrue torsion 0, actually infinity, but we can just take the reciprocal of that. And then finite torsion gives you some sort of filling obstructions. There's then a notion of planar torsion, worked out by Wendell, which is similar to Jrue torsion, but it's set up such, again, that the 0 level is exactly the over-twisted ones, and then tries to work its way in. So these are sort of very topological theories. And then there's an idea of algebraic torsion, which was set up in the world of symplectic field theory by Lachov, Wendell, and I'll write an SFT next to that. So this is something which, again, takes the second approach, starting from the world of pseudo-holomorphic curves and whatnot, and trying to work down. And so you can get some of these cobordism-type inequalities from it. What you don't get, of course, is a completely rigorous theory because it depends on symplectic field theory. And so this was redone by Michael Hutchings in the world of his embedded contact homology that I'll say a little bit about later. Again, giving you some partial results along these lines. So what I want to talk about is a way of redoing this algebraic torsion, but now in the context of Heegaard-Floer homology rather than embedded contact homology. And we'll see along the way why this might be a more reasonable setting for things. So where can we put up Floer theories? Big board. So what do we have? Floer theories of three manifolds. There's, of course, three main contenders for these. There's the original Seeberg-Witten, Floer theory. We should write everybody's name, I guess. Kronheimer and Mrówka, which we won't use at all in the talk, but should be written up there. There's then Heegard Floer due to Oswath and Szabo. And then embedded contact homology that we already mentioned due to Michael Hutchings. And then, of course, it's now known that these things are all isomorphic to one another. We have, so say in general, we have the first one due to Taubes. Make sure we're getting these right. And then two independent projects which showed the other two sides of this around the same time. The first one due to, well, the one up here at least, due to Kuplan, Lee, Taubes, and then this one here due to Kolan, Kijini, and Honda, just for completeness. So what are these? Of course, they are theories, homology theories, which give invariants of M as a smooth manifold. They're defined using some extra geometric information. And they each contain, given, or they each assign to a contact structure on the manifold a contact class which gets sent one to the other through these various isomorphisms, and we'll just call it C throughout the talk to refer to any of these. And so this algebraic torsion up there in embedded contact homology we can just view as a refinement of the contact class, as this thing enjoys a few of these properties. What do we know? That contact classes that for, let me say it like this, such that if C is over twisted, the thing vanishes. And if C is fillable, it does not. So it already satisfies a few of your criteria, and then you can refine it in some way to get more of them. So that's the goal. So my plan for the rest of the talk is to first sketch how this works in embedded contact homology, and then we want to use the setting of this Kutluan-Lee-Taubes isomorphism to see how to port this over to Heegard-Floer homology, and then possibly prove a theorem and give some examples. What do we need to know about embedded contact homology? Not very much, but just enough to give an intuitive idea of what's going on. ECH. What is it? Well, it has a chain complex, ECC. So first of all, let's say it like this. It starts from the data of a contact manifold, but slightly more refined data, this time of a contact form, as opposed to the structure. Remember, the structure is the kernel of the form, so this is sort of more information. From this one gets a Reb even vector field, which is just the one that sits in the kernel of this is R. D of lambda, and then we normalize it by lambda to be 1. And then so the homology theory is the chains are generated by collections of these, certain orbit sets. And you have a differential which then counts in the symplectization the manifold across R, pseudo-holomorphic curves interpolating between orbit sets at the top and at the bottom. So I have some orbit set up here, I'll call theta plus, and the differential sending it to some theta minus on the bottom via some pseudo-holomorphic curve we'll call C. So that's just the general shape of the theory without going into any details at all. So what can we do with this? Well, what can Michael do with it? Again, all of this is due as part of it to Michael Hutchings? Well, to each such curve which is being counted in the theory, he assigns a bunch of integers. So first of all, there is the ECH index itself. So we're counting ECH index 1 curves, by far the most complicated part of the definition, and I won't say anything about it. But he also defines a couple of variants of this. So we have the first one, J0 of the curve. So this is, again, it's a variant of the ECH index, which is meant to bound the complexity, the topological complexity of the curves being counted. So give some sort of a filtration. So we can say this is a variant of the IECH, the ECH index, which for nice curves, so let's say for the case of an embedded J-holomorphic curve with ends at distinct orbits, and we should put of multiplicity 1, I guess, just to be sure about everything, is just the Euler characteristic, well, minus the Euler characteristic. Okay. So in some sense, it's like the topological complexity of the thing. And then we can change this a bit and define something called J plus, which is just J0 plus the number of positive ends of the curve minus the number of negative orbits of the curve. And what is this good for? Well, just a couple of facts. This last thing here, well, first of all, it's additive under pasting curves together along orbit sets. And then it's also non-negative, which properties then mean that we can use it to decompose the ECH differential as, let's say, boundary 0 plus boundary 1 plus boundary 2 dot, where each of these is just counting curves of the proper J plus. So we'll say boundary I counts curves whose J plus is 2I. J plus is always even for whatever reason. Well, what else? And then from additivity, we can get that, since the thing squares to 0, we find that these mixed terms, if you fix some integer, or natural number k, the sum over all I plus j equals k, boundary I, boundary j, should also give us 0. So boundary 0 squares to 0. Boundary 1, so let's say boundary 0, boundary 1 plus boundary 1, 0, et cetera, from which some room, one can cook up a spectral sequence, which we will call the ECH spectral sequence, because that's what Michael calls it, which, again, started from this data of the manifold and a contact form. And there's a choice of an almost complex structure in there as well, but it turns out not to depend on that. And so what is this? Well, it's roughly, you can say that the 0 page is just the chain complex. And then for additional pages, ek greater than 0, this is just the homology of the previous page. Minus 1 with the k minus 1th differential. And then, having done this, we see that if the contact class disappears in the ECH, well, it's going to be killed off at some page of the spectral sequence. And one can ask when, and define then the algebraic torsion AT of MC to be minimum k, which is not negative, such that contact class vanishes on the, I guess, k plus 1th page of this for some contact form, right? So that's the choice we made here. Unfortunately, though, this doesn't, it's not independent of the choice of contact form. So this is its major shortcoming. So this was worked out, I think, back in 2006 or so by Michael, was then sort of pulled out to say something about this torsion of Latchev and Wendell, and then just got left behind. As we'll see, one can push it over into the world of Floer homology and maybe get something better. So that was, to some extent, my introduction. Any questions about anything? Maybe a little bit fast.
So the difference between theta plus and minus, is that an orientation on the element?
No, it's just what it's the differential sending theta plus to theta minus in that picture. That's all I meant. By this, the pseudo-holomorphic curve is, yeah. Right.
Something like the minimal complexity
Yes. Yeah. Okay, where are we? Right, so what's our setup? So we're down to our particular setup. And so we're using now the data of an open book decomposition to keep track of things. So let me remind you what that is. So an open book decomposition of our manifold M. It's just a topological thing. So it's a pair of a surface compact surface with non-empty boundary and some element of its mapping class group. So just some isotopy class of self-diffeomorphisms, which is the identity near the boundary. And from that data, what we want, such that we can decompose M as the mapping torus of phi. So what's that? We take sigma, cross it. Let's make this explicit with 0, 1. Paste the ends together using phi. So let's say P1 gets pasted to phi of P back at the beginning. So the mapping torus then has, on the boundary of this thing is just the boundary of sigma across the circle, right? Because phi is the identity near the boundary, so we can close it off by pasting in the boundary surface cross D2, alternately just collapsing each of those circles. So decomposition of M in this way is an open book decomposition. Get my board back. So what then do we do with this? Actually, I want to use a whole board for this because this is going to be a big picture. Oh, I should say I can do that over there. so what's the connection of these things to contact topology? Of course, there's this theorem of Jrue, which tells us that contact structures on a manifold M up to isotopy are in one-to-one correspondence with open book decompositions on the manifold up to a stabilization operation that I might say something about later. This is the Jrue correspondence theorem. Right, so what do? Well, we start with an open book decomposition. And in fact, we want a little bit more. We want to also have a basis of our surface. So open book decomposition and a basis, which just means this is a collection of disjoint arcs. Disjoint arcs such that if we cut along them, we get a disk. A fairly standard object. So from this data, we get a couple of things. Well, first of all, of course, we get a contact manifold via the Jrue correspondence. And any contact manifold, for any contact manifold, we can find such a triple. On the other hand, we get, in a fairly natural way, a Heegard decomposition, right? If you look at this mapping torus and think about collapsing these disks down to points, well, you can think of sigma cross 0, 1/2. It's just a two-handle body. Sigma cross 1/2, 1, another two-handle body. And this basis then cross 0, 1/2 and cross 1/2, 0 gives us the compressing disks in the two Heegard pieces. So we can encode that as the surface S, which is just going to be the boundary of, what did I say? Sigma across 0, 1/2, let's say. That's your Heegard, your splitting surface. And then it will have on it collections of curves alpha and beta, where alpha then is just the boundary of B cross 0, 1/2. Beta in the other one, boundary of B cross 1/2, 1. And then there's some base point that we put in here because we're going to turn this into a Heegard Floer. We're going to use it to define Heegard Floer homology. Now, on the other side of things, we have this construction due to hook on the Taubes, the setting of this isomorphism I had written up earlier between Zeeberg-Witten Floer homology and Heegard Floer, in which they use a Morse function adapted to this Heegard splitting to build up a manifold Y, which is just topologically, it's the connect sum G plus 1, where G plus 1 here is the genus, or G, sorry, is the genus of the surface here. You, in a way that's guided by this Morse function, you basically, you excise a little ball around each critical point, and then you tube these together with copies of the interval cross S2. And so you obtain this new manifold, and you cook up on it what's known as a stable Hamiltonian structure, which you can think of as just a generalization of the of a contact form, which in particular is robust enough to give you Reeb dynamics, and so you can run the ECH machine in a slightly simpler form. And what they get out of it, they label, well, one of the things they get out of it, we call little ECC0 hat, the chain complex associated to this thing. And so what is this good for? Well, on the other side of my board, I can use this Heegard complex to build the hat complex of Heegard Floer homology. So we should probably say which some end of this we're interested in, the one associated to the spin C structure, which comes from our contact class. And we find that these things are isomorphic due to, again, these three people. So this is the setting of this at least a part of this isomorphism. So this group down here, probably most people know at least a little about it, but we're going to use the cylindrical reformulation of this Heegard-Floer homology due to Lipschitz. That's how he spells it. In which we're looking at, so what is it? So it's generated now by intersection tuples between the alpha and beta curves. So some point, let's say x, x1, x2, xg, such that there's some permutation, some element of the symmetric group on G letters, such that each xi sits in alpha I intersect beta of sigma of I. So the generators are just tuples of this form. And then you have a differential, which is counting. I don't have room left on my board. Which counts now pseudo-holomorphic curves into this, what did I call this? S, the Heegard surface cross D2. And so if we have such a curve called CL for Lipschitz, which is such a curve, this is such that if we look at the projection down onto S, what we see is some, what we call a domain D, from which we can then read off properties of the curve CL. So D here is just it's a sum of regions in S. So these are just pieces of S minus the alpha beta curves. So what? Well, what do we have? So the way this isomorphism up here works, we can run, so we're running an embedded contact homology over here. It's a particularly simple setup in which the curves are of this nice form. They're of the type that satisfy, we can use J, we can just set J plus to be minus the Euler characteristic, or set J0 to be minus the Euler characteristic, and then J plus as I had explained it earlier. And we see we have a one-to-one correspondence between curves that are being counted here and curves that are being counted here. So we can define a J plus over here, which we can then read off from the Heegard region in a fairly reasonable way in a Heegard diagram. So what do we get? From this, we get another, we run exactly the same machine. I won't go through it again, but I'll call it this time the Heegard-Floer spectral sequence. We haven't, I don't think, come to any agreement on what this should be called, but this is what I'll call it from now. And this one depends on this data that I had started with up there. And so we define a notion of algebraic torsion in exactly the same way. But now we're taking a minimum over all of these triples, which are somewhat better behaved than than this contact form. In particular, we know sort of well understood how to switch bases around, and in the space of open book decompositions, as I had mentioned earlier in this theorem of Jrue, these are all related by the stabilization operation. So we have a slightly simpler list of things to check. As I mentioned, this is work in progress. We're making progress. We are checking these things. And everything seems OK. But again, work in progress. Caveat. OK, so what can we do with it? And how can we sort of see it down in the Heegard diagram? Well, no, yeah, what we're checking is whether or not we can check it from an arbitrary triple.
So you hope this minimum is not necessary?
Yes.
Then why would it be necessary on the easier side?
Well, things are different there. I mean, here this isn't. I mean, it's necessary in the ECH side because it's known that the deformations of the contact form that preserve the contact element or the contact structure can change things. But in our simplified setup, this is a much simpler thing here. The ECH complex is much simpler, and so you have a.
So in the end, you expect that your number, which is a single number, will be the minimum over all choices on
Yes.
the other side.
Okay. In any event, it's a much simpler thing to check than it was over in the full collection. Okay, so what? We want to read this off from D. Given a curve, we'd like to be able to read off its J plus and then understand something about the spectral sequence from that. So let's just write down how to do that. We had said that in our setup here, we can just set J plus of our curve in ECC to be minus the Euler characteristic of the curve plus the number of positive ends minus the number of negative ends. The way this setup works here, curves over here, well, let's say curves over here come from curves over here by adding on G one-handles. So for a curve CL here in the Lipschitz picture, we have minus the Euler characteristic C plus G plus the rest of the stuff. And then Lipschitz tells us how, from the corresponding domain D, to read off the topological information of the curve overhead. And I'll just write down a final formula. This is 2 times nx plus D plus nx minus D minus 1 plus plus minus x minus. Okay, so what is all this stuff? So D is the domain that we get from projecting down to the S factor here. These numbers are then nx plus. So nx plus, x plus and x minus are the two generators. So it's going from x plus to x minus. In x plus, remember x is just a point on the surface, an intersection point. So we can take the average of the coefficients of D around the point. And I'll do an example in a minute. And similarly for x minus. And this notation over here just means we're looking at the number of cycles in sigma, the permutation that was used, that is determined by the indices of the intersections. And so it's a nice, easily understood formula. And we can use it to prove a theorem. Right, but things that are being, yeah. I mean, you can actually use it. Right, but I'm assuming we're having something that's being counted. Okay, so what? First obvious thing one might want to check is that, well, if your contact structure is over-twisted, this thing should be 0. Right? I'll just use algebraic torsion to refer to our version of it. So I need to find, I need to see the contact element being killed off, the contact class being killed off in the first page, right? So by differentials, which are counting these 0-level curves. And how do I do this? Well, I use the following fact to let's say like this, from results of Eliashberg. Actually, the theorems that I've already mentioned in Jrue. we can always find an open book decomposition which supports Xi, i.e. is associated to it through the Jrue correspondence. Open book decomposition for Xi, which is a negative stabilization. So let me tell you what that is. So what does it mean to be a negative stabilization? Well, you can just see this fairly visual way. If we start with some open book decomposition, which we'll call, so it has some surface, some mapping class associated to it, and we consider the extra data of just take some arc, a properly embedded arc in the surface, and then add a one handle to this thing, such that the attaching sphere is just the endpoints of the arc, and then extend the core of the handle over the arc you started out with to get a simple closed curve in the surface, which I'll call S. Then the negative stabilization here is just the new surface, and we want to compose the monodromy with a negative then twist about S. So we cut it, turn it 360 degrees in the negative direction, glue it back together. So topologically here, you're just, in terms of the 3-manifold, you're taking a connect sum with S3, so you're not doing anything, but it's an over-twisted S3. So the result, again, has to be over-twisted, right? The over-twisted disk sort of comes along for the ride. So what? From what I said over here, I guess I won't say why this is true, but, well, it's not too hard to see why this is true, right? Because over-twisted contact structures, as we said, they're in one-to-one correspondent. They're the same thing as homotopy classes of plane fields. And if I know what the effect of this stabilization is on the invariance of the plane field, well, in fact, there's this z-valued invariant of plane fields which gets shifted by 1 when you do this. So you just choose the homotopy class which gets shifted to the one you want, which is the same thing as an over-twisted contact structure. Take an arbitrary open book decomposition for it, do this to it, and then you have the one you want. So I have an open book decomposition of this type. And I can choose a basis on it, which then includes this, the co-core of the handle that I added on. Yeah? Why do you need Eliasper to get this? I guess you don't. Well, no, you need to know that the homotopy classes, that each homotopy class has a unique chi in it, right? Well, because otherwise, when you push forward, you might end up in the same homotopy class but with a different contact structure. You need to know both that it's over-twisted and you end up in the right homotopy class. Okay, well, fine. But for a simple explanation, I can use this. OK, so we could just say then from Jrue's framework, we get this. OK, so let me focus in on a neighborhood of this core and see what's happening. So it's a properly embedded arc. I stick it in my basis. The image of it under my mapping class here, well, phi, of course, is the identity on the handle. Tau S inverse then just pushes it off to the left in this sort of simple way. And then if I think about what's happening in the Heegard diagram, I should say that everything I'm doing here is really, you can find it in work on the Cousins and Madic where they define the contact class from an open book decomposition and then discuss about what happens in the case of something which is not right-veering. Anyways, let's just give them credit for the method of proof here. So what happens in the Heegard diagram? Well, you're thickening up the page. sense. And so your co-core then becomes this alpha curve, which we'll call alpha 1. And then the image of it becomes the beta curve, which we have to isotop in some nice way. For reasons that I won't get into, so this is beta 1. And to each element in your basis, you have, in doing this, you get some preferred intersection point, which for this one I'll just call x1. And Honda-Kazazamadic show that the tuple you get by doing this represents the contact class. Of the contact structure you started with. So we need to see this as a boundary in the homology. And you do, right? If you just take this thing and say, let's call that y1, then we see a domain which we can work out, or Honda-Kazazamadic work out, does actually correspond to a holomorphic curve in the complex. So let me just write that down. We see there's a boundary of y1, x2, xg is exactly what we wanted, x1, x2, xg, which is then, as we said, the contact class, so the thing vanishes in homology. And we can then check the J plus of this thing. But so we call it D. What do we have? We have 2 times the average of the coefficients around this point, which is 1/4, plus the average of the coefficients around that thing, which is also 1/4, minus 1. And then what is the cycle associated to this thing? Well, formula up there. Well, every element in this thing is just alpha I intersect beta I, the way I set this up. And the same thing is true of yi. So the cycle in each case is just the identity plus g minus g, and we total that up, and we get 0. So we see it being killed on the first page of the spectral sequence, what we wanted. So in the last few minutes, I want to give example of a less trivial domain. And so this example is, well, let me just draw it up, and then I'll tell who it's due to. So we're working on an open book decomposition, which is planar, has 4 boundary components. And we're looking at a mapping class, which is given by taking positive den twists to each along these boundary parallel curves, and then minus 3 around that thing. And the basis we're interested in is this. So let me say a few things about the example before I draw it. So the contact manifold you get out of this, which we'll again call C, has a few nice properties. Well, as we would expect, it's tight and not fillable. Is tight, which we can see by work of John Baldwin. Wait, nope, sorry. The next part would have been due to John Baldwin. This would be due to work of Ito and Kawamura. Its contact invariant 0, so it's not fillable. This would be due to work of John Baldwin. And all of this was noticed by, we should write, Conway, Calotti, and Kulkarni. OK, so why are these things true, if you really want to know? Well, it's tight because we have sort of sufficiently much twisting around the boundary components. The technical term being that the fractional den twist coefficient is greater than 1 for each boundary component. For a planar open book decomposition, that is sufficient to conclude tightness by these two people. And as for this statement here, we get it from this cap-off cobordism of John Baldwin, which basically just says that if you fill in a boundary component, then you get a map on the contact element going from the filled in one to this one. But if you fill in a boundary component, you see that this -3 is larger than this 2, and so you end up with something twisting the wrong way. And so by the same argument I gave up there, or just using Honda Kazazamachi's other work, you see that in the result, the contact class vanishes, so that in this one it must as well. Some brief reasoning. So what do we see? So I'm just going to focus on these two elements of my basis. The other one doesn't really come into it. I'm going to draw what happens. I think that's right. So you can see it, right? The domain sitting in there. Now, what is it? Well, it is, let me put some coefficients in here. 1, this becomes 1. This is 2. I can follow around me to 2. This is 2. 1, 1, 1. 1, 2, 1, 1. And this had a 1, right? Yes. OK. So what is this doing? Well, it's sending, am I right about this? Yeah. The tuple, which is this point, and then all the other ones are just this preferred intersection that we don't see, to this guy, and then all the intersections that we don't see, which is, of course, just the contact class. Now, we know that something has to be killing the contact class from over here. And we just reason by looking at all the possible domains in this picture that this is the only one that shows up. So this domain has to come from some holomorphic curve. And we can calculate its J plus from this formula that I gave you. And I don't want to bore you with the details of it, but what do you get? Around this thing, 2, 4, 6, 7 fourths. Around the other thing, plus 1/4, plus 1/2 for the other end, -1. And then your cycle length, again, all of my intersection points are in alpha I intersect beta I. So my cycles are both going to be the identity. And if I've done everything right, 7, 8, 9, 10 over 2. Is this right? Oh, yeah. 5 minus 1, yes, is 4. And we can work out that the algebraic torsion of this thing then has to be 2. So, right. OK. It can't be 0 because it's not over-twisted. So we're seeing sort of a non-trivial example of all of this stuff in action. And that's really all I wanted to say. So thank you.